So our speaker today is a returning speaker. Dr. Greenberg has given several talks, and always just a fantastic talk. Gary earned his PhD in developmental biology from the University of College in London. He then became an assistant professor at the University of Southern California, engaged in research and teaching. In 1990, he began inventing and building 3D light microscopes for biomedical research. And if you've ever seen through them, they're really wonderful. You get this depth perception through a microscope. It's incredible. He's been issued 19 patents and is currently working on his 20th patent. Gary has captured extraordinary images through his microscopes, including living cells, grains of sand, flowers, and other ordinary things, or seemingly ordinary things. His most famous images are of the human pancreatic cancer cells through the microscope. They were used as special effects to portray the surface of the planet Krypton in the movie Superman, of the Christopher Reeve Superman.
Today our talk is about how telescopes and microscopes over the last quarter of a century, since about the year 2000, have totally changed our view of the universe, the world around us, who we are, and what we're made of. And this is what I'm going to be talking about tonight. So these telescopes and microscopes and things that we're finding out about, answering the big questions that human beings have had since the beginning. Things like, who are we? Where are we? Where did we come from? Where are we going? And who controls the universe? What are the laws of nature? So I want to look at this diagram here. You see on the left side, telescopes have shown us cosmic distances, what things look like, really large things look like from a very far distance. So for example, on the left side, these are images through the telescope of some of the first galaxies that were ever formed. This is about 12 billion years away. That's how far away that image is. Then if you look where it says macro, that's about 1 meter. So 1 meter is 39 inches. That's the macro world, the world we live in. That's the kind of stuff that we see. Now, if you go to the micro world, micrometer is a millionth of a meter. It's a thousandth of a millimeter. And then over here where it says nanometer or nanometer, those are nanometers of the size of molecules. And on the very right side, it's called an angstrom unit, and that's the size of atoms. All atoms are about the size of an angstrom unit. This is a picture of the origins of the universe. And at the other end of the spectrum, we see with microscopes like these are some of the biggest microscopes in the world. They get up to 1 million times magnification. So we can see what we're made of. This is hair here. This is human hair. Let's take a look what it looks like once we get up to about 5,000 times or about 100,000 times magnification. We're zooming into the hair. And those are cells. There's 3 cells there, and those are the colors that give. So the question is, and this is the question of the whole talk, how did human beings become such keen observers of the micro world? How is it possible we can see the ends of the universe and everything down to little tiny atoms? The answer is, it's the scientific method. And that's the first thing that I want to talk about is the scientific method. So this is Raphael's School of Athens. This is a painting. This painting is on the wall. It's a fresco on the wall in Vatican City. And all the various philosophers are there. You have Plato and Aristotle in the middle. These natural philosophers created the foundation for scientific method. It was based on observation, questioning, dialogue, and logical thinking. Now, Plato, on the left here, he was a student of Socrates. And Aristotle, on the right, he was the student of Plato. And Aristotle wrote about all kinds of things. And he believed the way you know something is true is either by ethos or authority, pathos, emotion, or logos, logical thinking. And for 1,500 years, his books were basically the primary ultimate authority. If people want to know what's happening, they would look it up in Aristotle. Now, the Renaissance changed everything because in the Renaissance, they added the idea of experimentation. Experimentation was the key to the scientific method because nature is the ultimate authority, not Aristotle. And the idea is experimentation is how you ask nature questions. That's what an experiment is. An experiment is designed to ask nature questions, and if you ask it cleverly, then you will get an answer. So I want to give you an example of this. Galileo versus Aristotle in gravity. Aristotle said that heavier objects fall faster than light objects. So Galileo said, well, is this true? Let's ask nature that question. He dropped a marble in a cannonball, and if Aristotle was right, it would be the expectation. Reality showed that they both fell at exactly the same time. Now, Galileo made these intricately designed scientific instruments to measure the speed at which little marbles rolled down inclined planes. And he from this, these different weights that he used, different weights of marbles, different sizes, different inclined planes, he was able to measure the accelerating force of gravity. And he said that everything falls with the same accelerating force. And that force is equal to 9.8 meters per second squared. Doesn't matter if it's a hammer or a feather.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
So now I want to talk, this is part one about telescopes. Telescopes were invented in Holland about 1600. And about 10 years later, Galileo made one, and he decided to look at the skies with it. Now, telescopes were not used to look at the sky. Telescopes were used as spyglasses. The Army and the Navy used them. Nobody ever thought, well, let's look at the sky with it. But Galileo did. He discovered, these are his drawings of the moons in Jupiter. He discovered the 4 largest moons of Jupiter, and that they were orbiting Jupiter. Nobody ever knew that. And he looked at the phases. He looked at Venus and saw that during the year, Venus has phases like the moon, proving that essentially Copernicus's heliocentric view of the solar system was correct, that our solar system, the sun is in the middle, not the Earth, which is what everybody had thought for a long time. By 1900, it appears that we live in an island universe. We live in a universe that basically is made of the Milky Way. And that's a picture of the Milky Way we're seeing. If you could see them all, there's about 100 billion stars. There's about 200 billion stars in the Milky Way. That's half of it, about 100 billion stars. So Edwin Hubble, in 1918, was the principal investigator on the Mount Wilson 100-inch telescope. This was by far the biggest telescope that had ever been made, and it allowed us to see things we've never been able to see before. So here's the amazing thing. He looked in outer space, and there used to be these fuzzy patches in outer space that nobody knew what they were. And when he looked at the fuzzy patches, they turned out to be entire galaxies of their own. Huge galaxies with billions and billions of stars. So that's pretty amazing. And what he discovered, that everywhere you looked with this telescope, it doesn't matter where you look, there were galaxies everywhere. And these galaxies were all moving away from one another. He measured the speed at which they were moving. And he realized that distant galaxies, or the more distant the galaxies were, the faster they were moving away from each other than the closer ones. So this proved that that the universe was expanding. All these galaxies were moving away from one another. This set the stage for what we know now as an expanding universe. So scientists thought, what if you calculate the expansion in reverse time? What if you mathematically put everything in reverse? What happens? They all come together, and they all come together about 13.8 billion years ago into a single spot called the singularity. And the Big Bang, at that moment, space and time was created. In a moment, all the laws of nature were created. And in the very beginning, there was a cosmic inflation. It was the fabric of space-time that was expanding. And the echo of the Big Bang was photographed by that spaceship. And this is what it looks like. These were the microwave background radiation and the irregularities of the early universe. And it's these irregularities that caused the formation of stars and galaxies in the universe. Now, the earliest atomic elements in the universe, and they were mainly hydrogen. It was mainly hydrogen gas. Hydrogen has one proton. And there was some helium that has two protons. There was a tiny bit of lithium, which is number 3. But mainly it was hydrogen, ton of hydrogen. In fact, that's an understatement. It was more than a ton. Gravity started working on these clouds of hydrogen. And they made the clouds of hydrogen compress and come together. And they compressed so great by the force of gravity that the clouds of hydrogen went into nuclear fusion. Now, what that means is that 2 atoms of hydrogen, if you slam 2 of those together by gravity, they actually come together and fuse to make 1 helium atom, an extra neutron, and a ton of energy. That's what a hydrogen bomb is. These are continuous hydrogen bombs. That's what stars are. Stars are thermonuclear reactions that are continuous hydrogen bombs. Now, the force of gravity took all of these stars that were forming, and they came together. They were moving. These stars were moving, and they formed into galaxies, where thousands and actually billions of stars started circling each other in these galaxies. But here's the interesting thing. We recently discovered something called dark matter. Now, we thought that it was gravity that made these stars hold together to make these galaxies. But it turns out there isn't enough mass in the stars of the galaxy to keep the galaxy from spinning apart. There needs to be more matter there. Otherwise, these galaxies would spin apart and we would not see them. So they proposed an idea of dark matter. And that dark matter is around these galaxies, and that extra matter is what holds them together in the shape that they are. And although we can't see it, dark matter is invisible, you can see how light interacts with dark matter. So this is a picture of the ends of the universe, or the beginnings of the universe. And you see this picture, you see these long streaks here, long streaks. They are distortions of galaxies. Those are pictures of galaxies that have been distorted by dark matter. So these images literally show that dark matter was behind these streaks there. So dark matter is an attractive force. And on the other end, we're finding out for the last few billion years, the universe is expanding faster than it has been for the last 10 billion years. It's been slowly expanding for the last 3 billion years. The expansion has sped up for something we call dark energy. And the dark energy is a repulsive force that is making our universe expand. Now, here's the interesting thing. This dark energy and dark matter were only recently discovered. It turns out that 95% of the universe that we live in is dark energy and dark matter, and we know virtually nothing about, very, very little about them, other than that they're attractive and repulsive. It's only 5% of the universe is stuff that's lit up, or stuff like gas and clouds and dust and rocks and stuff like that we can see. So there's a lot yet to discover in the universe. So, part 2, microscopes. So microscopes are about the worldly things that we see here. And this is the periodic table of elements. This is all of the elements that exist in the universe. So it starts with hydrogen on the left, which is number 1. It has 1 proton. Way over to the right is helium. It has 2 protons. Lithium over the left has 3. Beryllium has 4. Boron has 5. Carbon has 6, and so forth. These are all the elements, because there's no half a proton. There are only, and the ones that are at the bottom here, the ones that are at the bottom, when you get to the heavier ones, they are radioactive and they're very short-lived. They decay. So where do these elements come from? Because the stars were really just made of hydrogen, turning hydrogen into helium. But what happens when large stars explode in supernova or hypernova, the explosions are so great that it forces all of these atoms together to make all of those different elements of the periodic table. All of these elements here are made by the explosion of supernova and hypernova. I'm going to give you an example of what these things look like. So this is a ceramic. Ceramic is what the Earth is made of. It's like clay and so forth. This is a spark plug made of ceramic. It's a very good insulator. And this ceramic insulator is used on spaceships returning from outer space because they insulate so well. And you can see here why they're such good insulators. It's layer after layer after layer of insulation. And so they're unbelievable heat insulators. Now we're getting into, see that straight line? There's one crystal on the right and one crystal on the left. This is the crystal of alumina. And we get to about 1 million times magnification, the entire world changes. All of a sudden, what we see, every one of those dots is a single atom of either aluminum or oxygen. Now inside of that we can't see anything because it's basically mainly empty. But every one of those little dots was an atom. So the discovery of the microscope in 1600 revealed the underlying fabric of nature. Nobody had any idea that there was a microworld out there until this guy, Robert Hooke, built himself a very cool little microscope. This was an interesting guy. His nemesis was Isaac Newton. To say they hated each other would be an understatement. This is the first time a scientist had a job. And he came out with a best-selling book called Micrographia. And in those days, there were no cameras, so you had to be a really good artist. And he created images of all this stuff that he saw. This is the flea. Nobody had any idea that fleas had beards and looked this way. And he showed what flies looked like and their compound eyes. And people were amazed. It was the first and last bestseller through microscopes. So a few years later, Anton van Leeuwenhoek saw Robert Hooke's work, and he got pretty excited about it. And he figured out how to make a lens that was really good. And he made this little handheld microscope, and you can see it's on the right. The lens he made is the size of a drop of water. You can see the lens, and the end of that little pin is where he put the specimen. And he put the microscope right up to his eye, and he looked through that little tiny lens to see what was there. And this guy discovered that the microworld is alive. He discovered protozoa. Nobody had ever thought that there were microscopic organisms. He discovered bacteria. They're even smaller. That's pretty amazing because he just had enough resolution in his microscope to discover bacteria. Bacteria are really small. He discovered that blood is made of cells, made of red blood cells. And then what must have really shocked him is he looked at spermatozoa and saw these little things running around. So for the next couple hundred years, microscopes were made and used as parlor microscopes. They were entertainment. So you'd go to someone who was an aristocrat, and you'd have a garden party, and they'd bring out the microscopes, and you'd look at bugs and rocks and flowers and all kinds of things. It wasn't for another 200 years that microscopes were used in biomedicine. And this guy here, Virchow, is Austrian, about 150 years ago. He realized he could use his microscope to diagnose diseases. This completely changed the world. It was really quite incredible. It changed the world of medicine. And today we still have it. If you have something questionable, you go have the pathology done. You draw the blood. You take a biopsy. Then this guy, Louis Pasteur, he was another amazing person about 150 years ago. He came up with the idea of the germ theory of disease. In other words, diseases are caused by germs. And what he meant was bacteria. And he started, at that time, or just before his time, this is a Peter Bruegel painting of the plagues. And the plagues were they just killed literally millions of people. I think half of Europe was wiped out during the plague. This was some serious suffering. So here this guy comes along, and he uses his microscope to find out the bacteria that causes leprosy, anthrax, typhoid fever, all of these, and he makes an immunization against all of these and saved millions upon millions of lives. Now, here's a really important thing I want to try and make you understand. All of life is made of cells, and that the cell is the basic unit of all life. There is no life that isn't a cell. And the most important thing was that all cells come from the multiplication of previous cells. Now think about that for a minute. All cells. They just don't, life just doesn't pop up out of nowhere. All cells. So here's some cells that I photographed as a graduate student. You can see there's a dividing cell in the middle. It just separated its DNA. And here is, there's two cells there now. On the bottom left, there's another cell that's dividing. You can see on the bottom left it's starting to form its DNA. It's synthesized two sets of DNA, and in a second now it's going to divide, and there it goes, and there's going to be two cells there. So this has been happening without stopping for 4 billion years. This is what I'm trying to make you understand. These cells didn't come from nowhere. They came from previous cells, and that goes all the way back to 4 billion years, to what we call Luca, the last universal common ancestor. So the story I want to tell you about is the extraordinary journey of the first living cell, from Luca to Homo sapien. Now this was a miraculous conception, the creation of life on Earth 4 billion years ago, from rocks, gas, dust, water, meteorites, asteroids, comets, and lightning, all inanimate objects. And this is what the Earth looked like then. The moon was very close to us, much closer than it is now. Volcanoes were everywhere. The oceans had 1,000-foot tides. This was not what would be a hospitable place. But this was the environment that caused the creation of life. And what happened was atoms formed organic molecules. Organic molecules are molecules of carbon. Carbon, hydrogen, and oxygen. So when you take organic chemistry, it's the chemistry of carbon. Because carbon has a way of hooking up with all kinds of different other elements and atoms. Because they form chains and they form rings. And these rings and chains, the way carbon works, they can hook up with all kinds of things and make very, very complex organic molecules. These are simple organic molecules here. I'm going to show you some more complex ones in a minute. So these molecules organize themselves into living cells that could do work and reproduce themselves. Now, this is a pretty heavy concept. This is the environment and it was probably in the deep oceans, by the way. These vents in the deep oceans is probably where first life came from. So hundreds of unique molecules were all working together. I want to tell you about a half a dozen of these very unique, amazing, miraculous molecules. DNA, amino acids, proteins, ATP, glucose, and lipids. So DNA and RNA, these are self-replicating molecules. They can copy themselves. Look at this, identical people. How's that possible? That's how powerful DNA is, the master plan. How can you have identical people? How can DNA be so powerful? How is that possible? And the reason is because DNA creates the proteins and the enzymes that make up all the structure of our cells and the tissues and all the working parts. That's how they're so, it orchestrates all of that. That's why they're so powerful. So proteins are chains of amino acids. These are some examples of them. So these amino acids are chains, they're thousands of amino acids long. And the DNA codes for these thousands of amino acids, and what they do is they come out of the ribosome in a long chain and they fold up. And they fold up into these shapes. It's called protein folding. And the way they fold up into architectural shapes that literally do things. The thing up on the right is a channel, a membrane channel that lets things in and out of the cell. The thing on the left changes ATP to ADP. We're going to talk about that in a minute. But these molecules are architecture made of thousands of little amino acids strung together and folded up like origami. And some of these are motor proteins. They do stuff like this, where you have enzymes and motors. Literally, most of the stuff happening in our body, this kind of stuff is literally happening. It's pretty amazing. It's bizarre, but true. How does that happen? How is it powered? All of this is powered by a molecule called ATP, adenosine triphosphate. Now you see this molecule has an adenine molecule, a little ribose sugar, and then it has 3 phosphates. Those 3 phosphates are like a charged battery. It's like a battery just waiting to go off. And when that last phosphate goes off, it releases electrochemical energy for the cell to do its work. All cells, all living cells on Earth use ATP to power their work. And where do they get the energy to make the ATP? It comes from food. It comes from glucose. And where do you think that comes from? That comes from photosynthesis. So we all know this formula 6CO2 plus 6H2O, and light gives you sugar and oxygen. So here's the deal. Food is miraculously made from carbon dioxide and water. It's made out of inanimate objects. It's like food is made out of thin air. It's truly miraculous. So you got 6 atoms of carbon dioxide, 6 of hydrogen, a little bit of sunlight, and those are reorganized into glucose and 6 atoms of oxygen. Now what glucose is, it's stored solar energy, because it's the solar energy that allowed the reorganization of these molecules into that structure called glucose. So that's like a battery. Food is stored solar energy. Here's what happens. The opposite of that is eating and breathing. The reason we eat and breathe is this whole reaction goes into reverse. So we eat glucose and we breathe oxygen, and the oxygen burns the glucose and turns it back into carbon dioxide and water, and it releases ATP. That's where we get the energy to do everything that we do. So that is the beauty of this whole system. It all circles back again. Now you may notice we can't hold our breath for very long. That's because our demand for oxygen to get this ATP is really high. So we need food and a lot of oxygen. Where does all this happen? This takes place in the mitochondria of cells. This is a single connective tissue cell blown up very, very large. There's a nucleus on the left. And you see these worm-shaped objects that are moving around? Those worm-shaped objects are in mitochondria. Every cell is filled with them. So 4 billion years ago, over 1,000 different types of exquisite molecules, these organic molecules, wrapped themselves up inside a cell membrane, and that was how life was formed, the ignition of life for the first time. And the cell membrane had to communicate with the outside world and with the inside world. So it controlled the traffic of chemicals into the cell, such as through these channels here. These are membrane channels. It controlled the traffic of things out of the cell, so it could keep a homeostatic balance. And also, more importantly, it was filled with receptors. The cell membrane is filled with very sophisticated cell membrane receptors that sense the outside of the environment. They sense the environment. They're the eyes and ears of the environment, and they tell the cell how to respond in order to survive. So this is the first idea that cells must have some kind of awareness. All these cells have come together, all these molecules have come together, and these receptor molecules are sensing the world and guiding the cell in conjunction with DNA, and the DNA telling the cell what to do in relationship to what these receptors are telling the cell what's around the cell. So here's the big question in biology. More than a question, I say big mystery. The big mystery is, how did this happen? How is it possible that thousands of these exquisite molecules came together 4 billion years ago and created the first cell? How did it create Luca? How was that possible? We have pretty much no idea, to tell you the truth. It's truly miraculous, and we're a long way from understanding that. I've just been getting into this idea of how this happened. It's mind-blowing. It's a zillion to one. It's a zillion to one that this happened. But there's a zillion planets, and we're one of those. So we might be the one. So this was the emergence of Luca 4 billion years ago. These are molecules on a mission, and their mission was to survive, multiply, and evolve. They evolved. If they didn't evolve, they wouldn't be around any longer. And some of the first, most successful ones were cyanobacteria, these blue-green algae. They're still here. They're still around. And they have fossils. We've seen fossils from these over 3.5 billion years old in Australia. Now, for 3 billion years, life on Earth was only single-celled microscopic life, like this paramecium. That's all there was for 3 billion years. So if you expect to go to outer space and see life in other planets, bring a microscope with you, because you're going to need it. That's what you're going to need to see it. Now here's the amazing thing. Multicellular life didn't happen until 3 billion years later, and it was a quantum leap in the evolution of life on Earth. Now take a look at this little arc of evolution. So the Earth and sun ignited 5 billion years ago. And about 4 billion years ago, the first microscopic organisms. And for the next 3 billion years, it was only microscopic organisms. Until you get to the very top, about 1 billion years ago, you can see things like corals and sponges. Those were the first multicellular life forms. But then, about 500,000 or 600,000 years ago, about 500 million years ago, there's what's called the Cambrian explosion. All of a sudden, in fact, the Earth just came out of what was called the snowball Earth. The Earth had become a complete snowball. And then the volcanic activity built up because it was blanketed, and the Earth became warm again. And all of a sudden, all of these life forms, multicellular life forms, every plant, every animal, every bacteria, every microscopic, we were all descendants of this one cell called Luca. It was only this one cell that made it. All the other ones died out, if there were other ones. One cell, all of us are related. Let me just show you how related we are. If you look at embryonically at fish, amphibians, reptiles, and birds, look, humans start with gill slits and a tail. We all do. It's only later in embryonic development that we start to differentiate into the actual species that we actually are. So cellular specialization is what multicellular life was all about. Every cell has a job to do. There were thousands of different types of cells, and they now all work for the good of the organism. Think of all the types of cells that are needed to make all of our organs and tissues and cells work. So, some cells are dispensable. For example, if you look at this little gecko's toes, the cells between its toes were programmed to die at a certain point in development so the toes could be formed, because they started off as paddles, and then the cells between died and they formed the toe. So cells are dispensable. They come and go in a multicellular. It's about keeping the organism alive, not an individual cell. And the key to all of this are these embryonic stem cells. These are living embryonic stem cells. These stem cells can become any of the specialized cell types in the body. For example, they can become heart cells. These are the heart cells. These are 5 heart cells here. And when the heart cells touch each other, they all beat in unison. Then there's these nerve cells. These are live nerve cells. They're communicating in distance from place to place in the organism. And this is incredibly important for a large organism to be able to communicate quickly. They're always looking for new connections. Then there's cells of the immune system, because from the very beginning of life, the war was on. It was one organism trying to kill or eat the other organism or infect the other organism. So this is what happens. This little macrophage, you see that white thing? That's a bacteria. It's going to grab it. There it is. It ingests it, and it's going to digest it. That happens all the time in our body. Now here's some really cool cells of the immune system. This one on the bottom that's moving quickly, that's a natural killer cell. And it can kill virus-infected cells and tumor cells without any learning. The ones on top, you see the 2 darker cells on top moving around? Those are memory lymphocytes. Those are the lymphocytes that get activated when you take a vaccination. So if you had a COVID vaccination, you'll have many of these cells running around your body that are sensitive to COVID. And if they run across a cell that's infected with COVID, they'll jump on it and kill it. That's how before they kill it, they'll clone themselves and make millions of them, and then they'll kill the cell. We have sensory cells all over the body that are sending information to the brain. And all this information is painting a picture of our surroundings. And it does a pretty good job. Pretty good job indeed. And it all happens automatically. We don't have to think about it. All this is happening automatically in our body. So everything in our body is happening on autopilot until something goes wrong. So, part 3. This is the last part, human consciousness. So here's the question. What is consciousness? Why do we have consciousness? Why aren't we just biological robots? That's the big question. We have trillions of cells working together to produce the experience of consciousness, but we only have a stream of actual awareness of consciousness. We're unaware of all the processes that take place that create the consciousness that we have. So what is consciousness? Well, we use a lot of words for consciousness. There's a lot of different flavors. Today, I want to talk about living consciousness, collective consciousness, communal consciousness, and artificial consciousness. So what's an attribute of consciousness? It's an attribute of awareness of a self, an awareness of being and feeling. So what does it feel like to be? Sort of the idea, I think, therefore I am, Descartes' famous line. So, question is, do only human beings have consciousness? Well, do dogs have consciousness? Any of you have a dog, I'm sure you'd say, yes, dogs do have consciousness. How about this ant colony? Do they have a form of communal consciousness? How about this beehive? What's the consciousness level of these bees all working together for the good of not only the organism, but the good of the species? How about these bird migrations? What consciousness is controlling the flight of these birds and the schooling of these fish? Does these little protozoa have consciousness? Look at these little guys. They're single-celled microscopic organisms. You can't see them without a microscope. But do they have consciousness? So here's the big question I have. Does a living cell have consciousness? Let's go back to this living cell. Look at all what's happening in a living cell. We're going to go closer. This is really close to this. This is as close as you can get with a light microscope. Look at all the activity happening here. There's mitochondria, little things moving around. It's an unbelievable beehive of activity. So the question is, this whole molecular dance, how is this happening? How are these little molecules being moved from place to place? Well, it's all a molecular dance, and here's how they move. Look at this here. There's a myosin molecule, which is a motor molecule. It moves along an actin railroad track, bringing along with it, this happens to be a packet of endorphins from place to place. So a cell, just one cell, is a delicately balanced, interconnected web of information. More information from thousands of molecules all working together, just inside one little tiny cell. So my feeling is that consciousness is an emergent quality of life. That the cell, the consciousness is the basic, that all cells have consciousness. That's where it really comes from. So I want to have you look at this. This is 3 little heart cells. And they're going to beat. This is just before they die. I got my camera. I saw these great 3 heart cells beating. I wanted to photograph them. Got everything set up. And I get it going. And after the first beat, they died. But I want you to see a couple of things. Before they die, this is a beautiful interconnected web of information. There it goes. There's the first beat. And then on the second beat, they're going to go fuzzy. Look at this right there. They go fuzzy, and they go belly up. And now they're dead. They've lost, and they're going to fold up into essentially little bags of molecules. So these little bags of molecules, they're the same molecules as they were 10 seconds ago, but they aren't connected by this interconnected web of consciousness. So do these cells come together to make higher forms of consciousness in multicellular organisms? So is consciousness, I believe, is a meta-language. A meta-language that gives meaning to the molecular dance of life that we have. So what is a meta-language? A meta-language is a language that describes another language. So let me give you an example. These computers we're using right now and our phones, this is the language they use. They use zeros and ones. But we aren't real good at using zeros and ones. So we had, this guy Gates come up with Windows, and Windows is a meta-language which deals with the zeros and ones and gives them meaning so we can manipulate them and deal with them. That's what a meta-language is. That's, to me, what consciousness is. So nerve cells integrate even a higher level of consciousness. This is the very tip of a nerve cell, as close as you can see, a living nerve cell. They're always looking for new connections. These nerve cells aren't dividing, but they're always looking for new connections. As you listen to me and learn something, your nerve cells are making new connections. Here's one single nerve cell from the cerebellum of the brain, back of the brain. The cell body's at the top, and it's got hundreds and hundreds of little branches. And if you look close at one of these branches, here's looking closer at one of these branches, you can see that they're called dendritic spines. And every one of these branches has little spines on them. You see these little marks. Every mark there is a place where that cell is making a synaptic connection with another cell. This cell is making thousands of connections with other cells. This is the level of neural networks that we have in our brain. It's absolutely mind-boggling. So did Luca have a form of proto-consciousness? I think yes, that Luca did have. Or was it just a robot? I don't think that Luca was a robot. I think the reason it did evolve and into all of life is because it wasn't just a robot. So is consciousness in our DNA? Look at this little guy here. After he hatches, you know the first thing he does? Goes right to the water. It's right in his DNA. This is just automatic. So my question is, what does it feel like to be a bacterium? Does a bacteria have consciousness? If you were a bacteria, what would it feel like? So consciousness, I feel, has evolved from bacteria up to all these multicellular forms. This is the little worm, planaria. This little worm is the first organism that has a brain. It has 205 brain cells. What is consciousness for this little guy with 205 brain cells? Or what is consciousness for this little rat? Much more complex brain. Or how about the consciousness of this elephant? Well, what's clear when you ask these questions is that consciousness is species specific. I don't think there's any question about that. You know, there's dog consciousness, and there's human consciousness. So I want to talk about human collective consciousness. We're going to end with this idea of human collective consciousness. So that's a network of shared knowledge and awareness. And this all started with human society with storytelling. And from the very beginning, we were always storytellers. Language and storytellers. We had art, music. These were the ways that we communicated our consciousness through music, through writing, and mathematics. And all this information were stored in places like the Tower of Babel or the library at Alexandria. And these were made by scribes. In these days, they weren't books, but we had scribes that would take this information and write it down, and they'd store it in these huge libraries. Now, people didn't read or write. Most people didn't read or write, so they didn't have the advantage of knowing what that information was. It was only the aristocracy or the kings and queens that had that information at hand. But then here comes this guy, Gutenberg, comes up with this idea for a really cool press, and now the information is being spread. People started to read. It changed everything. And now with the internet, sadly people stopped reading a little bit, but all of human collective consciousness is in our pockets. Look at this thing. I can't help but bring it out. Look at this. It's all here, right here. Everything that humans know is right here, at our fingertips. It's bizarre. It's unbelievable. I still have a hard time to believe it, but it's true. It's all there. You can look it up. So how about AI? What's going to happen with artificial intelligence? Everybody knows this is coming, or I should say it's here. How is it going to affect our lives? Will artificial intelligence change our human collective consciousness? Yes. The answer to that is yes. But how is it going to change it? We know that in medicine and drug discovery, it's going to have gigantic benefits. Already, computers can diagnose better and treat better the patients than an individual doctor can. Now, these are proteins and enzymes and some chains of proteins. What's going to happen is that AI is going to be able to actually design these proteins that will be able to do things in medicine that things have never happened before. They'll be able to make nanoscopic machines that are unimaginable, that have never happened before, because they can literally use DNA to make these little tiny things and use AI. AI is solving the protein folding problem. Remember I told you that DNA makes amino acids into these long chains, and the long chains fold up into these shapes. But people can't predict what these shapes are because the possibilities are too large. AI is not figuring out how to predict the shapes of proteins to make things that have never been made before. Artificial intelligence is going to totally change our education, thank God, because what we do now is we teach to mediocrity. We teach to the middle. We forget the high end. We try and raise the low end up higher. We have to stop doing that. We have to teach people at their own pace to bring out their greatest potential. This is what is going to be happening with artificial intelligence in education. How is education going to change evolution? There's this thing called CRISPR, which is a way of editing DNA in a really cheap, really easy way. We can change our own genomes. We can literally design our children. That technology literally exists today. It's not legal. It's happened in China already. It's not legal. What's going to happen in the future? So the AI, the benefits are enormous, they're game-changing, and the risks are enormous, and they're game-changing. How are we going to survive these potential, unbelievable disruptive forces and these incredibly positive forces? Who is going to take advantage of the positive forces? So is it going to be Star Wars? Sadly, what's going to be happening in AI is going to be the good guys against the bad guys, just like it's been for a long time. So how are we going to survive and evolve? How is human consciousness going to survive and evolve during this time of AI? We're going to need a moral and ethical compass that have been shown by many of our religions and philosophies. We have to start embracing this. But more important, we have to understand and cherish and embrace our humanity, our storytelling, our music, our art, and our sports. These are all things that make us really human. These are the things that are the characteristics of our humanity. But if AI totally takes over, we are going to need meaningful work and meaningful play. If we don't have meaningful work and meaningful play, things could get really bad for human beings. So, 4 billion year journey has taken place from Luca, from the depths of the primordial ocean. Luca has gone to the moon and back. Quite amazing. This one little cell, 4 billion years ago, evolved to go to the moon and come back. The question is, will our lack of emotional intelligence put an end to Luca's journey, or at least for human beings? Well, here's the answer. It is not the strongest of the species that survives, nor the most intelligent that survives. It is the one that is most adaptable to change. So there you go. And here's one of my favorite poems. To see a world in a grain of sand. Some of you have seen my pictures of sand before. And there is a whole world in a grain of sand. It's true. This is the grain of sand from the moon. This grain of sand was formed about 3.5 billion years ago. And it hasn't eroded away because the moon does not have oceans. It doesn't have atmosphere. Things that happen on the moon stay on the moon. They don't get changed. Okay. So, are there any questions? Because I have a lot of questions, I'll tell you that. I definitely have questions. How in the world did life emerge on Earth? So the question is, how do we know that we all came from this first cell? Is that the question? So the answer is they came from Luca. And this was 1 billion to 1 happening, where thousands of molecules came together, wrapped themselves around a membrane, and said, voila, I'm a living cell, and I'm going to start. It's bizarrely improbable. But that cell that did make it, all cells since then have all been made of the same components. They all have RNA and DNA. They all use ATP. They all use ribosomes. They all use the 22 amino acids out of 50 of them, out of 80 of them. They're all left-handed. We all are made of the same components. So it evolved. All of the basic components are the same, all life, whether you're a bacteria or an elephant or a plant. We all are made of the same parts. That's how we know we all came from the very first cells that existed. What we can observe is we're all made of the same stuff. That we can. What we don't know is how that happened. We have not even a clue as to how that happened. When I say it's miraculous, when I say it's 1 zillion to 1, I'm not kidding you. It's a zillion to 1. And then the whole idea of multicellular life, that's 1 zillion to 1. The whole laws of life change. Instead of now a cell just looking after itself, now a cell it's dispensable. It's looking after the environment. It just takes on one job. How did that happen? That's a quantum leap right there also. But the way we know we're all from one cell, all the parts are the same. It's like, let's say, take automobiles. They all have tires, they all have engines, they all have steering wheels, they all have batteries, they all have transmissions. It's all the same parts. So we know they originated from an original idea. The question is, what about these other life forms that don't use oxygen and don't use carbon? These early life forms, extremophiles, they use sulfur. Well, they use oxygen. They use sulfur dioxide instead of carbon dioxide. But they still use ATP, they still use all the other stuff. And they're still around. If you look at Yellowstone, these extremophiles are still there. They haven't gone away yet. That's how successful they were. But still, they're made of the same stuff. But they used, to make their ATP, they were making their ATP out of the hot vents, which are sulfur dioxide rather than carbon dioxide. Yeah. So the question is, we can go back to the beginning of life and we know that that's a real miracle. But if you go back another 13.8 billion years, there was the formation of the universe in the Big Bang. How do we know that happened? Well, it's likely that it happened because when we look at the expanding universe and we mathematically look at what happened in reverse, we can see that it all goes back. Also, we have telescopes that can literally see what it looked like 12 billion years ago. So some of these pictures I showed you, they're pictures. The light took 12 billion years to get to the telescopes that took the pictures. So we literally can see what it looked like then. And we can see the first galaxies that were, by the way, our galaxy, the Milky Way, was one of the first galaxies that were formed. I should say parts of our Milky Way are some of the first galaxies that were ever formed. So we're kind of in the middle of this whole thing. So we presume it deductively, because if you take all those movements and put it in reverse, they all came together. Also, particle physicists and astrophysicists, they've worked out the details of this stuff. The question is, in the very beginning, were all those elements there? And the answer is no. In the very beginning, it was pure energy. You know the famous formula E equals mc squared. This is Einstein showed that energy, E, equals mass times the speed of light squared. It means that mass and energy are interchangeable. Mass and energy can go back and forth. One can be changed into the other. In the beginning, it was pure energy. Then it started to be turning into mass, very, very quickly into mass, and it was plasma. It was so hot there were no electrons, there were no protons, there was all subatomic stuff that didn't, and it wasn't until it took about 300,000 years before it cooled off enough that we got that picture of light, of the echo of the Big Bang, and then atoms started to form, and the protons started to form. And the first atoms that formed were only hydrogen and a little bit of helium, tiny bit of lithium. By the way, lithium is a very rare material that we're going to be fighting over in the future because the batteries are made of lithium. You notice that lithium is number 3 that means it's really light. So if you want a battery and you want it to be really light, it's going to be lithium. That's what's happening. So in the beginning, no. It was only hydrogen came later. Then hydrogen and helium hydrogen started making helium. And then in the explosion of these stars, they caused all the other elements to happen. They just smashed them together. Yeah. It represents the biggest mystery of the universe that ever happened. All I know is it started with pure energy turning itself into mass, and energy and mass are turning themselves back and forth all the time. Well, that's a really interesting question. Does the explosion of stars create order or chaos? It's both. This is the interesting thing. Obviously, an explosion is a huge amount of chaos, especially if you're anywhere near it. But the order that's created out of it are all the ordered elements of the periodic table. They're all created. So that death is a moment of creation. So that death and chaos that happens in these explosions that are just mammothly huge. You can't really imagine how much energy is released in the supernova at one point in time. And all that energy is so great that it forces these atoms together to create all those atoms of the periodic table. So it's a powerful creative force at the same time that it's a powerful destructive force. So it creates very organized elements. All those organized elements are created out of this destructive chaos. This is what happens in life also. You know, chaos and destruction, the phoenix rises out of the ashes, so to speak. So question is the universe expanding or is matter shrinking? So the first time I heard about this whole thing, I was in high school, I think. I was a precocious young man. And my teacher said, well, if everything is shrinking or expanding, the rulers are doing the same thing. Our measuring sticks are doing the same thing. So it's a hard question to tackle because of what I just said. The measuring sticks and rulers would be expanding and contracting the same as, maybe it's pulsing and we don't even know it, but all the rulers are pulsing too. Who knows? I don't know. But our way of measuring it would be changing at the same way in the same rate. So the big question is about big bangs. Some people believe that there are an infinite number of big bangs. Other people think, well, big bangs come and go. At one point, you know, there's still a discrepancy. You know, there's this fight between dark energy and dark matter. Dark energy is making the universe expand. Dark matter is making it contract. I don't know if we know the answer to that yet. So if dark matter takes over, the universe will literally shrink down to another new Big Bang and explode again. So the answer is we don't know, and it's anybody's guess, because all we can know is the universe that we live in. We can't know the universe before us. Yes, it's the brain, well, or is the environment piloting? So the question is our brain piloting us? Is that? Yeah, more of a comment. That consciousness. Here's the interesting thing. Our consciousness doesn't seem to guide us very much. We only have. Here's the thing that I see about consciousness. We only have consciousness in our mind when we attend to something. So, for example, we wished our brain were guiding us as much as we are. I think we're guided by a lot of other things that we're not aware of. So our conscious awareness, we're only aware consciously of what we attend to, and we only attend to a little bit. Think of all the stuff that's happening in my body right now for me to be able to do what I'm doing, for all of us. It's bizarrely complex, just in one cell. In one cell is bizarrely complex. Our brain has no control, no understanding of it. So our conscious understanding is really like a drop in the ocean, and our brain kind of does its best to try and sort out what our surroundings are. But if you don't attend to something, you know, a brick can come from the top and hit you and you won't see it. So it's only what we attend to that we are conscious of. So that's why I was saying I become more conscious of things about my body as I get older, because as you get older, you get more pain. So, you know, things all of a sudden light up for you when you're in your body. So the question is, was the Big Bang alive? Was that a form of life? So a lot of people think that consciousness is in everything. So if you believe in animism, which you believe that consciousness is in everything, like this table, everything, then you would believe that the Big Bang was a form of consciousness. But it wasn't a form of life. Life is what I was talking about using organic molecules to do work, to multiply, survive, and evolve. That's what I'm talking about what life is. And that's, so I've been talking about living consciousness. But many people, as I say, believe in animism, that everything has consciousness. But my feeling is, if you believe that everything has consciousness, that puts the end of the argument. There's nothing more to talk about. Okay, have you guys had enough? Thank you. Thank you, thank you.